Okay. I didn't get a lot of responses from the text message, but as I looked over the notes, I did want to just go over a few problems that you already went over, just to recap to make sure that you guys were comfortable with them, to maybe give you an alternative method from maybe what had been represented in the notes that Ms. Vaca had showed you. Um, so that I don't even know if I'm saying her name right. I call her Deb. So if I said it wrong, do not be upset with me. Just to make sure that you guys kind of got the memo. And then if you struggled, then hopefully this is an alternative method that can make things make a little bit more sense before we move on, because I don't want anyone to feel completely lost and kind of abandoned since I've been gone. So the first example I wanted to go over is actually number 3 on the notes that you have already done and turned in, but everybody, we're going to write it down anyway. The example is 2 times the cube root of 48. And so that is very shiny. So just a reminder, cube root just means what multiplied by itself 3 times. So square root is what multiplied by itself twice. Cube root is what multiplied by itself 3 times. And so the way that was stressed on the sheet was looking for perfect cubes, but I wanted to make sure that you guys had that factor tree method as another option, and so that's what I'm going to go over in these extra notes for you. So for the cube root of 48, we're going to keep that 2 as a coefficient. We're not going to ignore that. We're going to say that 48 is 2 times 24. 24 is 2 times 12. And then since I broke down the 24, I'm going to kind of scribble it out. So if you guys remember, we've done this before. This is kind of old news. 12 is 2 times 6. Since I broke down the 12, I'm going to kind of scribble it out. And then 6 is 2 times 3. And since I broke down the 6, I'm going to kind of scribble it out so it doesn't confuse me. Now, this too, I'm going to kind of cover this original problem up with my finger because this is not part of the factor tree and I don't want to get confused. So when I'm dealing with a cube root, instead of circling pairs, I circle triples. So I'm going to look at a triple of 2s. I'm going to circle my triples, and then I will underline my leftovers. So when I write the cube root of 48, it's going to be 2, and then a leftover 2 times 3 is 6. And then I still have the 2 in the front. So the final answer is 2 times 2 makes 4. 2 times 2 is 4, cube root 6. And that gives you the same answer as if you did the problem looking for perfect cubes. If you looked for perfect cubes, you would say, oh, the perfect cube in here is cube root 8. So you would say, oh, that's 2 times the cube root of 8 times the cube root of 6. The cube root of 8 is 2, so 2 times cube root 6. So you get the same answer, you're just using a factor tree method instead of the cube looking for the perfect cube method. The next example I'm going to do was example 9 on that same sheet. I know you don't have it because they're in a pile on my desk, but I'm going to reference it anyway because it might feel familiar. So we've got square root 32x to the 4th, y to the 9th. The factor tree method even works when you have variables. You do the same thing. So this is a square root, so we're going to look for pairs. So 32, 2 times 16, 2 times 8, 2 times 4, 2 times 2. So I'm going to scribble out the numbers that I broke down further. Okay, so I've got a pair of 2s, a pair of 2s, and a leftover 2. Okay, now with my x's, I don't really write these out like a factor tree, but I do write them out. So I'm going to write out 4 x's. 1, 2, 3, 4. And y to the 9th, I'm going to write 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And then because it's a perfect square, I'm going to circle my pairs. and then I'm going to underline my leftovers. So anything that I circled, whether I'm circling pairs or triples or quadruples, that is always the thing that goes under in the front. The leftovers that I underline, that's always what goes underneath the third root or fourth root or square root or whatever. So I have 2 times 2 gives me 4. X times x gives me x squared. Y times y times y times y gives me y to the 4th. Okay, and then for my leftovers, I have a leftover 2. I don't have any leftover x's. I have a leftover 2 and a leftover y, and so then I get 2y. So you did this with our substitute as well. You did the perfect square method, and the perfect square method was to say, okay, my perfect squares inside this where we have the square root of 16, x to the 4th was a perfect square, y to the 8th was a perfect square, and then our leftovers were the 2 and the y. Now, if this does not resonate with you, then you can do this kind of factor tree method here, which honestly, I'm going to say this is what I do. Maybe not with this. I might use the perfect square method with the numbers, but I kind of think of it this way when I do the variables. All right, for my next example, I'm going to do the same type of thing, but I'm going to do it with a third root instead of a square root, so you can see that it still works. So cube root 56, r to the 8th, s to the 4th. Okay, so 56, that is 2 times 28. 2 times 28. That's 2 times 14, 2 times 7. Okay, so we've got a triple and a leftover. Okay, and then we've got 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4. Okay, so I'm going to circle my triples. And 2 left over. Actually, I usually do the leftover 2. I usually underline them individually because you have to multiply them together. So R and R, okay, and then I circle a triple, and then I underline. Okay, so now I'm going to have my cube root. So the stuff that goes in the front is the stuff that I circled. So I circled a 2. So I've got 2 in the front. I have R times R, so that's R squared, and then an S. Okay? And then underneath I have a 7. I have an R and an R underlined, so R times R is R squared again, and then an S. And so that is my answer. Okay? If you're thinking of perfect cubes, then you're thinking of sets of R that would go into 3. So our perfect cubes here, we were thinking of the cube that goes into 56 would be 8. So we had the third root of 8. And then we had R to the 6th, S to the 3rd. And then we had our leftovers. So we had the third root of 7. We had 2 R's left over, R to the 2nd, and then we had 1 S left over, S to the 1. So whichever way resonates with you is fine. I just wanted to make sure that people who did not really understand this method were able to do this instead. Okay. I wanted to do one that has a negative in the front. Well, inside. And kind of show how that works. So a third root. So real quick, let me get a calculator. So just a reminder that if you do a number to the second power, -2 to the second power is always positive. If you type it correctly, -2 to the second is +4, -3 to the second is +9. But if I take the number -2 and raise it to the third power, then I can get a negative answer. -3 to the third power is a negative answer. So that means that when you go through, here's how we do a cube root. When you go through, if you cube root -27, you actually get a negative answer in return because it says, what can you take and say, oh, something multiplied by itself 3 times is a negative answer? Well, it's a negative number. 3 negatives multiplied together gives you a negative. And so that's why you can cube root a negative, but you can't square root a negative. Because there's no way that we would multiply 2 negative numbers and get a negative answer. If you have 2 negative numbers multiplied together, the negatives cancel out and you get a positive. So that's how this can happen inside only a cube root or a 5th root or a 7th root. It can happen with the odd numbers. So these negatives can happen with the odd numbers. It means that you have a negative answer. And we know otherwise, oh, negative answer, but only with the odd roots. We know that otherwise, if it was an even root, if it was a 4th root or a square root or a 6th root, we know that that negative means that it's an imaginary answer because that's something that we've studied already. Okay? I'm going to say that in parentheses, otherwise. Okay. So I'm going to do the same thing that I have done with the other problems. I'm going to do our factor tree. And so 81 is 3 times 27, I believe. Let me just double check. Yes, it is. Okay. And then that's 3 times 9. That's 3 times 3. And so we've got 3 3s and a leftover 3. And then p times p. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Goodness gracious. Okay, so the p's are both considered leftovers because we didn't even have enough to circle a triple. And then I've got a triple, a triple, a triple, a triple. Okay, so I know my answer is going to be negative. I'm just going to put a negative in the front. And then with my triples, I've got a 3, no p's. And then q times q times q times q is q to the 4th. Then I can do my third root. I've got a leftover 3, and p times p is p squared. Okay. Now, there was even this strange problem that had y plus 3 in parentheses. And honestly, you're not going to see these very often, but I did like it. It was a 4th root, and it said y plus 3 to the 8th. And even this we can do with this method, y plus 3 to the 8th. What this means is that we have, write it with me, this is obnoxious, y plus 3, it has this 8 times. One, 2, 3, 4, 5, 6, 7, 8. Okay, and then because it's a 4th root, we're looking for sets of 4. One set of 4, another set of 4. No leftovers, so that means we don't even really have to write a root because there would be nothing to go inside of the root. This would be a perfect, not a perfect square, not a perfect cube, a perfect perfect. Somebody figure out what it's called and tell me what it is. It's perfect, whatever it is, it's perfect. So we have y plus 3 times y plus 3, which means that our answer is y plus 3 squared, which we could leave as y plus 3 squared, or we could write it twice and FOIL it out. I'm going to go ahead and just leave it as y plus 3 squared. Okay. All right. So for today's assignment, I have kind of backtracked and said, let's calm today. Let's not go to the next step because the next assignment is a little bit more difficult. I wanted this to sink and settle a little bit and give you guys some time with it. So I wanted you to take these notes, and then we're going to pause and not move on for today. Okay, so I've looked through the assignment. These ones are just simplifying. I've compared them to what you guys did already. They're significantly easier than the other assignments you've had. The strategy for these is just to multiply together. I'll go ahead and just talk briefly maybe about number 4 on this one, negative 3 root 22 times 4 root 2. So when you're multiplying two radicals together, and you probably got this, but I'll just reiterate so we make sure that we really have it. When you multiply two radicals together, you multiply the coefficients. So we're going to multiply the negative 3 times the 4, and we're going to get negative 12. And then we can only multiply what's underneath the radical if it's the same type. So if it's a square root, you can multiply it by a square root. If it's a cube root, you can multiply it by a cube root. So here, 22 times 2 is root 44. And then from there, you are not finished. You now have to simplify that radical before you can continue on with the problem. So I'm not going to finish that for you. I'm going to let you finish that one. The same is going to be true for all of those in the second portion of that punchline worksheet. For problems where you're adding and subtracting radicals, if we look at a problem over here like number 2, this problem, 5 root 2 minus 3 root 2, this one's ready to go because the radicals are the same. They just have different coefficients. So you have 5 root 2's, you're subtracting 3 root 2's. If you have 5 and you take away 3, that leaves you with 2 root 2's. So that one's done. That is the answer. I just gave you the answer to that one. However, a problem like number 3 is not ready to go. Root 12 plus 7 root 3, you have to simplify the root 12 before you can do the problem. So root 12 would be root 4 times root 3. So that's 2 root 3. So you have 2 square roots of 3 plus 7 square roots of 3, and then you can add those together to see how many square roots of 3 you actually have. So, and those obviously get more difficult as you continue. So it is possible that maybe when you get to a problem like number 9, maybe all 4 of these cannot be combined. Maybe they don't all have the same base radical. Maybe 2 of them have square roots of 3 and 2 of them have square roots of 2, and you end up with 2 different radicals in the answer. Or maybe all 3 of them can be broken down and simplified to the same radical, and you can truly add all 3 of them together to get one answer. It kind of depends on the problem. Okay, so that is the assignment for today. Again, we're kind of taking a pause, just making sure that everyone's comfortable with what we've done.